Hello and welcome to today's physics lecture wherein we shall be discussing about the torque. Now as we are well through now with the Lorentz force, we know that actually like a wire or a conductor which is carrying electricity in a uniform magnetic field, it actually experiences a force. Now to understand that what a torque is and what is the torque experienced by a current loop in an uniform magnetic field B, we shall see it with the help of the diagram. First of all, obviously let us check that this loop is like this. It is in the form of a rectangle. This is a rectangular loop, right? Now let us give, say for example, P, Q, R and S, the 4 points. Let us name this rectangular loop. Now if this is a rectangular loop, obviously a current should be flowing through it, right? If the current is flowing likewise from QR to RS to SP and then back from P to Q, this is the flow of the direction of the current. Now over here the magnetic fields are present. Say for example the magnetic fields are like this. This is a uniform magnetic field, and these are the lines which shows that this magnetic field, these magnetic lines are actually flowing. So this magnetic field, this is represented by B, which is known as the magnetic field intensity, right? Now to understand it, we need to understand this diagram with the help of like 3D, right? So first of all, see that this is B or the magnetic field, right? So for example this green one. So let us check over here that this green one is the magnetic field as being shown. And this, like this coil, this rectangular coil, how this is actually like this. As we could see that this part is actually towards the reader and this part is away from the reader. So this will be like this, right? And there will be a certain angle difference between this B and this one. This is a loop, then obviously it has got some area, right? So if theta is the angle, so this is what? This is the plane of this loop PQRS, right? So the theta is the angle between the plane of this loop and this magnetic field. So we can say over here that this angle is, we can say as theta, right? This angle is the theta, or else we can say that this angle is also theta, right? And if this is the scenario, then obviously we should mention that, this is very important, we need to mention that what this theta is, that theta is the angle between which two. So we must mention over here as theta is equals to angle between B of all understand that this is the angle between B and the plane PQRS, not the angle between B or the magnetic field and the area vector, because the area vector will mean that this is a plane and 90 degree to that will mean the area vector. In many of the regions it is said that theta is the angle between B and the area vector. So if we are going to deduce that accordingly, it will simply give us a total different formula. Right now we are taking that theta is the angle between B and the plane PQRS, right? Over here, if we do observe and apply the Fleming's left-hand rule, we can observe that a force is going to act on this QR at this direction. This will be the direction of the force, right? So the force of QR, we can write it as, the force of QR will simply be equals to, we can write it as B I, let us take this one as the length, so we can write over here that QR is equals to PS, right? QR equals to PS equals to length, and over here PQ equals to SR, PQ equals to SR equals to, say, the breadth or B. So this will be, see, I, the amount of current that will be flowing through the entire loop will be the same. It would not vary, right? The B over here is said it is a uniform magnetic field. So on QR, the force that is being enacted in this direction will be equals to BI multiplied by the length of this, that is equals to L, multiplied by sine theta. This is the angle multiplied by sine theta. Say for example, we give it the equation 1. Now we find out the F for PS. The F for PS, if we apply the Fleming's left-hand rule, we shall find over here that this will be in this direction, right? This is, we can write as F QR. This is the F experienced, or the force experienced by this PS, is equals to B multiplied by I multiplied by what is the value of PS, what is its length, simply equals to L multiplied by sine theta. Now let us give it the second equation. Now closely observe that if we are going to draw lines, we shall see over here that the force QR and the force PS actually lies on the same line, which means, say for example, the force of 5 Newton, this is like they're pulling it down by 5 Newton, and this is also pushing it up by 5 Newton. Why? See, both are BIL sine theta, so they are same in magnitude but opposite in direction, and they lie on the same line. They are lying on the same line, which means that I am trying to pulling this pin over here, and I am trying to pull this pin from over here as well. But the pull are along the same line and of same magnitude. The pin won't move anyway, it will stay where it is. So we can say that this FPS and FQR actually cancels each other. Therefore, we can say that FQR and FPS cancel each other. Right? Now over here, let us check for the, say for example, PQ and SR now. Now if we are going to apply the Fleming's left hand rule for this PI, first of all see over here. This is the theta, right? For this QR and PS, right? Now over here, if you do observe that actually the angle between the length and the beam, as we know that over here we need to find out the angle between the length and the B as was indicated by the Lorentz magnetic force, and thereby we deduce this expression. It was like cross product. The length of this is along this direction or this direction, take it anywhere else. But where is B? B is simply in this direction, which means over here that if we do find out likewise that this is B and this is, say for example, over here, this is a B and this one is PQ, this one is say PS. So how will actually the PQ look? The PQ will look like this, and it will be mutually perpendicular to B, right? As we need to find out the angle between BL and B as was indicated by the Lorentz magnetic force, so we can write it out as PQ. The force for PQ is simply equals to BI, the length of PQ is equals to small b sine of pi by 2, or it is equals to the value of sine of pi by 2 is equals to simply 1. We can write it as BIB. Let us leave it as a third equation. Now the direction of this PQ will be along like this. The direction of PQ will be towards the leader if we are going to apply the Fleming's left hand rule. How? Like let us check over here. This is B, the forefinger like the index finger, the middle finger as I in this direction. Then where will be the force? Along the thumb. See, it is coming out of the paper or towards the reader, right? So we can write that this force over here, this is F of PQ, right? And now if we wish to find out for SR, the direction which we shall be finding out will be like this. This will be F of, say, SR, this one. And this force, actually the direction means it is going into the paper, going away from the reader. So, the magnitude of F SR will simply be equals to B multiplied by the amplitude of the current, that like magnitude of the current which is flowing through it, multiplied by the length, which means that this SR is equals to B, again sine of pi by 2, which simply is equals to BIB. Let us give the fourth equation. So we can see that this FPQ and FSR, they are same in magnitude but in opposite direction, because one is coming towards you and the other is going away from you, which means they are in the opposite direction. So likewise, as we have seen over here, that FQR and FPS actually cancel out each other. They will also cancel out each other, which means that actually there will be no force. Quite wrong. Try to open a tap. Say for example, if the tap is like this this and this, and you wish to open up the tap. If you are going to push it likewise, will the tap turn on? No. Always when we use our fingers to open the tap, we simply keep our fingers like this, such that this area will push this on this side and this one will actually move this side over here. But mind that the force exerted by this finger on this direction is equal to the force exerted by this finger on the opposite direction. The tap will turn to moon. Why? The magnitude of this is equal to the magnitude of this, which means the magnitude in this direction is equal to the magnitude in this direction. The force, which means that if they will cancel out, then there will be no force. If there is no force, there will be no work. Then how is it happening? It is as simple as that. If you did observe the tap, you will see that one force in the same magnitude is coming towards you, but the other force in second magnitude is going away from you, but they are not along the same line. Had they along the same line, such as like this, they would have cancelled each other. But now they are not along the same line. This is along this line and this is along this line. Over here, actually FP is cancelled out, FQ out, because they are on the same line. But over here, if you do wish to draw the line, you will find like this for FPQ, and for FSR you will find the line like this. Simple. They are not on the same line, but eventually these two lines are parallel. So always never cancel out one force saying that it is simply in the opposite direction and same in magnitude that they will cancel out each other. No. You have to look that whether these forces are actually lying on the same line or not. And if they are not lying on the same line, then they will form a rotation like this, and this simply is known as torque. So we can say now over here that this is one force and this is one force. Now we can say that torque is simply equals to, as we know that the work done was equal to the force multiplied by the displacement, the torque is similar to that for the rotational motion. The torque says that this torque will be equal to any one of the force, because the force are same. You take the force in any one direction. Say for example, I take the force, this one, FPQ. Now it will calculate the distance between over this point and the other force point, the perpendicular displacement. So we could say that if we take FPQ, the magnitude of this force of FPQ, which is simply equals to FPQ over here, multiplied by the perpendicular displacement from FPQ to FSR, FPQ to FSR, right? Now what will be the perpendicular displacement? Say for example now, if we wish to find out the perpendicular displacement, we draw a line likewise. If for example we want to find the perpendicular displacement from the point P on SR, one line is being joined such that this is equals to 90 degree, because this is the perpendicular displacement, right? Say for example we name this point as M. So the torque will be equals to this FPQ is equals to BIB multiplied by this is PS multiplied by the perpendicular displacement. See over here, this angle, if it is theta, then simply this angle will also be equals to theta. And what is the value of PS? The value of PS, as we could see, it is equals to L. So this value will be equal to L. If this is L from trigonometry, we know that this value of Pn now will be equals to L cos theta. So Pn will be equals to L cos theta. So multiplied by this Pn, which will be equals to VIB. Value of Pn now replaced by L cos theta. This will be L cos theta. So simply over here, if we do observe very carefully, this is B multiplied by L. For the rectangular portion over here, if you observe that the length, if multiplied by the breadth, it simply gives us the area of this plane, right? So this will come out to be equals to BIA cos theta. So the torque which we represent by this will simply be equals to BIA cos theta. And if this rectangular coil, if it is having, say for example, more number of loops, or say example n number of loops, then this torque will be equals to NBIA cos phi. Now we have observed, while we were discussing about the magnetic dipole moment, we did observe at that point that the multiplication of this current and the area is simply equals to M, or the magnetic dipole. So we can also write this torque as equals to N multiplied by the magnetic dipole moment multiplied by B cos theta. Now in many areas or in the references, you may find that the torque is equals to the cross product. Say for example, if N is not over there, only one single loop, then this will look like MB cos theta. But in many of the references, you may find that the torque is equals to the cross product of M and B, the M vector and the B vector over there, right? And the cross product of the vector M and B will shall represent as MB sin theta. So where is the flaw? We have written as MB cos theta, so it might be possible that I made some mistake over here. Or it might be possible that the reference what you are using, it may have made a mistake. No, none of us did make a mistake. While solving this kind of numericals, you do have to be very cautious that what theta you are measuring about. If the theta is equals to the angle between the B and the plane PQRS, then this will be the formula. But else, if you are considering, say for example, phi as the angle between B and the area vector. The area vector, say for example, this is the plane, right? Over here, this is the y-axis, this is the x-axis, so this is a plane. We have regarded this plane and B, the angle between that. But if the angle is between B and A, where would be the area vector? The area vector shall lie normal to this plane, right? At that time, if we do find out, say for example over here, the area vector shall like be this, that this is coming towards 0, and this will be, say for example, the phi. So this angle and this angle, they are completely different. If we do use this phi, then we shall see that this torque will be equals to, for a single lobe, this torque will be equals to mb sine phi, or the torque is simply equals to the cross product of the magnetic dipole moment and the B vector. So don't get confused about this. Just try to understand that what is the angle given. If the angle is between the area vector, this will be the area vector, right? If the angle is between the area vector and the B vector, use this formula. Otherwise, if you are given the angle this as between the B and the plane of the lobe as theta, then we need to use the cos theta, as this is the formula. Right? Thank you.